Hello there, Mr. Sutton here, bringing you this lesson on right triangle trigonometry applications. In this one, we're going to be finding missing sides and angles in triangles in a bunch of real-life situations, including finding distances and heights. Before we can do any real-life problems, though, there's some terminology we need to take care of, and that is dealing with angles of elevation and depression. So an angle of elevation is the angle between looking forward and looking up at something. So, for example, in this picture, the angle of elevation is the angle between looking at the top of the tree and just looking straight forward. So you can think of this as the angle between the floor and the hypotenuse. Now, the angle of depression, and depression you could think something that's a downer, right? That's the angle between looking forward and looking down. The angle between, I guess you could call it the ceiling and the hypotenuse. So here's a situation where you might have an angle of depression. Let's say you're in a lighthouse and you're looking down at a ship. Your angle of depression is the angle between looking forward and looking down. Now, it's interesting to note that there's actually kind of two triangles in here. You could also think of the angle of depression as being the same as the angle of elevation looking up at the lighthouse from the ship. So this angle here and this angle down here actually come out to the same thing. In general, it's helpful to think of these as always being angles between a horizontal line of a triangle and the hypotenuse of the triangle. So, without further ado, let's take a look at our first real-life problem involving right triangle trig. Let's talk about Mount Everest, which, as you may know, is the tallest mountain in the world. Have you ever wondered how tall? And how would you even measure such a thing? Well, good old trigonometry to the rescue, right? Let's say we have an observer 10 miles away, so this little green dot is the observer, and we're 10 miles from, let's say, I guess the center of Mount Everest, whatever that means. So using a homemade sextant, that's this little device here that you might have used in science class back in the day, just kind of, you have a protractor with a straw and a little weight hooked up to it to measure angles. So using this little homemade device, we see that the angle of elevation from your observer to the top of Mount Everest is roughly 29 degrees. Based off of this, we want to know how tall Mount Everest is. So I'll put a big X here on the height of this triangle, and I added that. There's not really a giant X chiseled in the side of Mount Everest, as cool as that would be. So let's see how we could find that height. So we're going to go ahead and find the height on this page. Now, as you might gather, the first step to solving these real-life problems is to be able to actually draw a diagram with everything in it. So here's the triangle that we pretty much drew on that last page. I have my angle of elevation, I've got my horizontal distance, and I'm looking for the vertical distance. So which trig function, since this is a right triangle, which trig function would help us out the most here? Pause the video, because you guys know SOHCAHTOA, and see if you can figure this out. All right, so using SOHCAHTOA, we have the adjacent side as the non-hypotenuse leg. We're looking for the opposite side. So opposite adjacent, that's TOA. So we have tangent equals opposite over adjacent. And in this case, we have tan of our angle, which was 29 degrees, equals our opposite side, which is that X that we're looking for, the height of Mount Everest, divided by our adjacent side, that's this 10 side here. Now, to solve for x, we just multiply both sides by 10, so 10 times tan of 29, and we know for this we will need the calculator. So, plugging 10 times tan of 29 into the calculator, making sure, as always, that we are in degrees mode, we press enter, and it's going to come out to about 5.5. Now, we were 10 miles away. The unit of distance is miles, so we're saying that Mount Everest is about 5.5 miles tall, which is pretty darn tall if you think about it. Here's another problem for you. So from the top of a tower, angle of depression to a flower on the ground is 74 degrees. Top of the tower is 90 feet above the ground. How long will a ladder from the flower to the top of the tower need to be? So pause the video, see if you can draw a diagram here, and then you might want to tune back in just to make sure we've got the same diagram, and then go ahead and solve the rest of it. All right, so for my diagram, since I'm dealing with angles of depression and looking down, I'm going to use an upside down triangle. So here we are. They said our angle of depression is 74 degrees. The angle of depression or elevation, it's always between the horizontal line and the hypotenuse. So I guess you could think of it as being between the adjacent side and the hypotenuse. So it's this angle right here. It's never this other angle. Now this is a little bit tricky though because of the way this triangle is drawn. They said the top of the tower is 90 feet above the ground. So the tower is right here. This is what you're looking out of. The tower is over here on the left. But the side of the triangle is over here on the right. This height of the triangle, however, is the same as the height of the tower over here. So I'm going to put my 90 feet over here, but we know that it really represents the height of the tower that's on the left. And they want to know how long will a ladder from the flower to the top of the tower need to be. So distance from the tower top to the flower, that's this hypotenuse right here. So that's my x. All right. So if you didn't get that diagram, you might want to adjust things and then pause the video again and solve for x. All right, so let's see what we have here. We've got the opposite side from the angle. We've got the hypotenuse. Opposite and hypotenuse, that's the sine function. So we write sine of theta equals opposite over hypotenuse. So that means sine of our angle, 74 degrees, equals my opposite side of 90 feet over my hypotenuse of x. And then to solve for x in this situation, we know we have to multiply by x and divide by sine of 74. So basically switch those. So we've got 90 over sine of 74, which we now need the calculator for. So there we are on the calculator, 90 divided by sine of 74. And that is 93.6, and that is going to be in feet. We'll do one more of these real-life problems to see if you've got the hang of it. So let's say you're letting out 50 feet of string on a kite, hovers above a point on the ground that is 20 feet away from you. This time we want the angle of elevation to the kite. So we're looking for an angle for the first time. Pause the video, give it a whirl. All right, so we've got our triangle. We're talking about angles of elevation. So I'm going to say a right side up triangle works the best here. We're letting out 50 feet of string on a kite. So here's you down here. Here's the kite up here. So that means your 50 feet of string is this hypotenuse here. And then the kite is hovering above a point on the ground that's 20 feet away from you. So 20 feet away from you on the ground is down here, this side of the triangle. And then we want the angle of elevation, so x is the angle here. All right, so which trig function makes the most sense here? Well, we've got the hypotenuse, so it's not tangent, and we've got the non-hypotenuse leg involved here, so that's going to be the adjacent side. Adjacent and hypotenuse, that is the cosine function. So we can write cosine of theta equals adjacent over hypotenuse. And this time we have cosine of x, the angle we're looking for, equals my adjacent side, my non-hypotenuse leg of 20, divided by my hypotenuse, which we said was 50. And now we know to get the angle in these situations, we have to do inverse trig. In this case, we need the inverse cosine of 20 over 50, which we need the calculator for. And just a reminder, we need to do second cosine to get cosine inverse. And then we've got 20 divided by 50. Enter for that. Comes out to 66.4. Now, don't forget the units on this. That's degrees, because that's an angle we're dealing with. So 66.4 degrees. So that's it for this one. It's been real. This is Mr. Sutton. Till next time, signing off, or co-signing.